In the first molecule, we began to learn something about the thermodynamics of molecules, but we haven't really paid too much attention yet to the details of those molecules and the details of their energies. We've talked about energy as basically a system attribute, but we know that that energy comes from the contributions of all the molecules that make up the system. What we want to do in this module is begin to fill in some of those details, and we'll need to distinguish between different types of motion. So let me try to illustrate what I mean by that. Let's consider a 3-atom molecule. So it'll be a triatomic molecule. Now if I were to write down sort of the kinetic energy of that 3-atom molecule, I could do it in great detail by simply writing, well, it would be the kinetic energy of the first of those 3 atoms, so I'll call that V1x squared, V1y squared, V1z squared added together and multiplied by the mass. And then I could add the kinetic energy of the second of the atoms, which has mass m2, so now it'd be V2x squared plus V2y squared plus V2z squared. And then I could add in the kinetic energy of the third atom, which would be the mass 3 times V3x squared plus V3y squared plus V3z squared. And I have now given a very detailed account of the motion of that molecule. Now, it involves a lot of variables, though. And in particular, there are 1, 2, 3, 4, 5, 6, 7, 8, 9 different components of velocity that are making up this kinetic energy. So 9 components of velocity. So we would say that this particular molecule has 9 degrees of freedom. It's basically got 9 different variables that can vary and adjust its energy accordingly. Now, it's pretty easy to see that if we're in a 3-dimensional space, a molecule of n atoms, this was of 3 atoms, will have a total of, and I'll use D to represent degrees of freedom, it will have a total of 3 times n total degrees of freedom. Well, it would be great if that's where we could finish, but I note that translational motion, which is this kinetic energy motion of molecules, it's just one of the ways that these atoms can move. And in fact, in this case, we could talk about the motion of a molecule simply by designating its center of mass. So I might call that those center of mass coordinates x, y, z, giving them capitals because they represent the center of mass of the whole molecule. And so there's only 3 of these, and so they would also have 3 components of velocity. So that means that translation really only represents 3 degrees of freedom for this molecule in space. So if it only has 3 degrees of freedom and yet there are 9 total degrees of freedom, what happened to the others? What other degrees of freedom are there? Well, one of the things that we can notice is that molecules can rotate. And in fact, they can rotate if they're a 3-dimensional object. So let's draw just some 3-dimensional object. And I'll try to give it some shading here so you give some 3-dimensional aspect of it. There are 3 axes about which it could rotate. So I'll call that x, y, and z. And so when it rotates, it could rotate about the x-axis, or it could rotate about the y-axis, or it could rotate about the z-axis. And any one of those would represent a particular degree of freedom. In fact, we could write the rotational energy, if we use basic physics, we could write that as equal to 1/2 ix, which is a moment of inertia term, times an angular velocity about that x-axis, plus 1/2 iy, angular velocity about the y-axis, plus 1/2 iz, angular velocity about the z-axis. And so in effect, I've got 3 rotational degrees of freedom that also contribute to the motion of this molecule. Now, it turns out that for rotation, it's not quite as simple as this. This is true for most molecules, but we do have some molecules that are linear. So if I have a linear molecule, let's draw that just like this, I don't have 3 degrees of rotational freedom for this. Let me illustrate this by drawing a plane that contains the molecule. This plane is sticking out of the page, and then another plane that's in the page that contains the molecule. So the molecule is on the intersection line between these two planes, and this molecule can either rotate in the vertical plane, like that, or it could rotate in this horizontal plane, like that. So we have 2 different types of rotational motion, but the one type we don't have is it cannot rotate about this plane. Why not? Because how would you tell that it's rotating? It's rotating about the axis that is along its bond axis. So whenever we have a linear molecule, we say that it only has 2 degrees of rotational freedom. Right, but we still haven't added up to 9 in this case. Right, I've got 3 translational degrees of freedom, 3 or 2 rotational degrees of freedom. What are the rest? Well, it turns out that these atoms can also move relative to one another. So what we will do is term this vibrational motion. So you can just think of it as vibrating like a spring would vibrate. It doesn't cause the whole molecule to move anywhere. It just is motion of the atoms relative to one another. And they make up all the rest of the degrees of freedom that we haven't accounted for yet. So if I have a nonlinear molecule, that means I would have 3n total degrees of freedom, minus 3 for translation, minus 3 for rotation, or a total of 3n minus 6 vibrational degrees of freedom. If I have a linear molecule, on the other hand, I'll have 3n minus 3 minus 2, or 3n minus 5 vibrational degrees of freedom. Now, this may seem like really trivial stuff that we're doing here, but it is important to keep track of how many degrees of freedom a molecule has, because as we're going to see, a lot of the energetic properties are going to depend upon knowing what those degrees of freedom are and how they distribute themselves among translation, vibration, and rotation. And as we go through the rest of this lesson, we're going to learn something about how those energies relate to one another and their relative magnitudes to one another.